All right, let's look at another example. We're going to look at inherited stature again. This is the actual data set and analysis conducted by Francis Galton, who was one of the major founders of statistics, along with R.A. Fisher and Carl Pearson. All of them were both biologists, but also kind of sociologists as well, and polymaths. They were all geniuses in of one sort or another. Francis Galton, in his 1885 paper, with his beautiful title, Regression Towards Mediocrity in Hereditary Stature, he invented this idea of a regression model. So let's look at his analysis, assuming that it's a random sample from a population. Let's conduct inferences on his regression coefficients. So this is the model on the full sample of data, right? So we have roughly 800 observations, and you can see that what he's doing is he's trying to predict the height of children based on an overall measure of the height of parents. And you can see taller parents on that x-axis, right, we tend to predict a greater height for children. Right? And we have a regression model with an intercept of 22.38 and a slope of 0.64. But let's look at the regression output. Right? When we conduct the full inferential regression test, right, we obtain this output. All right, you can see that we have the intercept and slope, but we also have a standard error and a t-ratio. And then you can also see that we have p-values. The p-values are annotated with asterisks. For both the intercept and slope, we reject the null of a zero population coefficient at the alpha 0.001 level. That's because there are 3 asterisks. You look at the significant codes below, and you'll see that those 3 asterisks indicate that our results are statistically significant at that level of alpha 0.001 level. So we conclude that parental height is a statistically significant predictor of the height of children. And intuitively, the idea is that we do not think that these regression coefficients are an artifact of random sampling, assuming that this is a random sample from a population. Let's look at another example. Let's look at life expectancy. So suppose you're working for the UN and you want to examine the extent to which population growth in percent predicts higher levels of life expectancy in years across a data set of countries. So you gather data from random samples of people from 63 countries. Our sample size is 63, and we're going to treat this as a random sample from a population. So here are the results. The x-axis is population growth. The y-axis is life expectancy. Right? Here are the results for the inferential model. Okay? You can see here that for both the intercept and slope, we reject the null of a zero population coefficient at the alpha 0.001 level. We have point estimates for the intercept and slope. We have a standard error, and we have a t-ratio. And the t-ratio is simply the point estimate divided by the standard error for each of those 2 respective coefficients. We can put that t-ratio on a t-distribution, and based on the location of that t-ratio on that t-distribution, we can obtain these p-values. In both cases, statistically significant for both the intercept and the slope, so we reject the null that the intercept is 0 in the population. We reject the null that the coefficient is 0. The slope coefficient is 0 in the population. So we say we believe that population growth in percent is a statistically significant predictor of life expectancy at the alpha 0.001 level. Now we're talking about statistical significance, but what is the substantive significance? Let's look at this model again. Okay? So here we have these 2 estimates. Right? Our focus in this case is on the slope, because the idea is we want to see, for every 1% increase in population growth, right, what is its effect on life expectancy? What is the relationship with life expectancy? So we're going to focus on that slope. And we should consider, well, these 2 coefficients and the slope coefficient, they're statistically significant, but what does it mean to be substantively significant? Well, look at the effect size. Right? Look at the actual coefficient itself and try to interpret that coefficient. The effect size is simply that point estimate. Try to interpret it. Believe it or not, a lot of researchers, they will focus on the statistical significance, so they'll look at those stars and they'll say, well, we either reject or fail to reject the null, but they do not focus enough on the effect size. So it's really important that you look at this, because it's one thing to say, oh, we think that this actually exists in the population, it's not due to random sampling variability. But it's another thing to say, well, okay, so if it exists in the population, all right, that's one thing, but is it a big effect? Is it an important effect? Is it a small effect? What kind of effect is it? That's why you should always look at the effect size, look at the point estimates, try to interpret them. So here we see that for every 1% point increase in population growth, we expect the mean life expectancy to drop by about 2.2 years. That strikes me as a pretty large effect. 2.2 years, that's a lot of life that we expect to decrease, right, as that population growth increases. So we can say these findings are not only statistically significant, but quite substantively significant as well. However, with simple linear regression and with regression models in general, keep in mind what it's really doing. Right? It is just giving you the mean of the outcome conditional on different values of x. Right? In this case, it's giving us the mean life expectancy conditional on different values of that x variable of growth. This is a danger with simple linear regression, or regression models more generally, is that it might be tempting to claim that population growth is somehow causing a decline in life expectancy, but we really don't know, because this is an observational study. It's just a bunch of measurements on population growth and a bunch of measurements on life expectancy, and we're using different values of population growth to predict the mean life expectancy. Right? We don't know if this is causal or not. It does suggest that we might want to look into the mechanisms, the processes by which we might think the population growth affects life expectancy. But this study itself, it's observational. In the same way that correlation does not equal causation, in a similar way, we can say a simple linear regression model is not necessarily a causal relationship either, because all it's doing is fitting a mean conditional on different values of our x variable. And with that, we've gone through a few examples of conducting statistical inferences on simple linear regression models.